Okay, guys. Hello, everyone. Hello. Uh, Today it's Wednesday, uh, and we have November 18. We have last lecture before the exam number 3. So I think other people will come. Our lecture will be short, but important because I really want to give you some kind of overview. So I recall, in fact, it is 6 lectures, 6 classes that left. Today, Friday, Monday, and 3 after the Thanksgiving break. And you will have your exam on Friday. Remember, it's and I encourage you again. So nothing is fixed yet, and entropy is really difficult topic. So if you did not do well at exam 1 and 2, you still a good chance. You still have a chance to recover because your exam 3 and final together is 50% of your score. You're in good shape. You can do it. Believe me, people do it. At the same time, if you got A for exam 1 and 2, again, nothing is fixed yet. Take it seriously, you may fail because this is a new topic. Again, your homework is due today. I hope most of you submitted it. If not yet, please do it very soon because tonight, no later than tonight, we submit our solution. You need to see the solution before your exam, right? You need it for Friday. And the best hint what you should do, it's uh, really go through your quizzes, your exams, your homeworks, especially for exam 3, through your homeworks, homework 7A and homework 6, right? At this point, let me share my screen and let me proceed with what I have here. And let us talk about let us have some kind of summary. And a week ago, last Friday, I did send you this. You may remember I sent you this kind of summary slides, right? But I encourage you to remember one thing. The worst thing you can do if you assume that these 20 slides is the only thing you need for your exam. Not at all. This is the last item you do when you're preparing. You should go through them Thursday evening or Friday morning. Do everything else. Homeworks, textbooks, lecture notes, videos of our lectures, which I will posted. Please make sure you understand it. Now, definitely, and also it will be my help session today at 5 o'clock at Zoom. Please come, please attend. I will try to address all your questions. What I encourage you to remember, what is your assignment, what you should do now. You after remember there were a lot of theoretical question, philosophical question in second law and in entropy in chapter 6 and 7. So your primary task now to be flexible, to manage them. You should deal with entropy in the same manner like you did with enthalpy, internal energy, volume, temperature, pressure, heat, work, and many other items. That is your task. Usually, it's like driving. You need to practice, practice, and practice. That's what you need. Now, if you remember, and I hope you remember, you did your homework, most of the problems you have in your homework, it's extension of previous problems. It's extension of chapter 4 for a closed system. It's extension of chapter 5 for open system, right? So we are not changing something. And when I gave help sessions yesterday, I realized that many people, especially not from my sessions, from other sessions, they confuse. They think it's something really new. They say, what formula I can use? Should my work depends on entropy or not? Remember, what we did before in chapter 4 and 5, we are not declining it. We extending this knowledge. And many problems you had at your homework, it was question A was find work output, find heat transfer. That was exactly problem from chapter 5 or chapter 4, especially chapter 4. But it was another question. Let's find entropy generation, entropy transfer. And then you should employ your new knowledge. So we are not declining it. We are not replacing it. We're extending it. And when I gave you balance equation for entropy, they are not instead of energy balance. They are in addition. It's system of equation. First equation, let's say energy balance is first law, entropy balance is second law. It's a system of equations. They are not replacing each other. So if you really see a problem and you don't know what to do, let's say, okay, forget about entropy and ask yourself, could I solve it without entropy? How would I solve it if there was no concept of entropy here? And you will know how to do it if you did well in chapter 4 and 5. Well, and what you should realize, the only point, that many systems we considered at exam 2, in fact, may not exist. I gave you in chapter 5 turbine and say, here is inlet, here is outlet, here is mass flow rate, here is workout to find something. And now you may know that this turbine may not exist at all. And you can prove it because of second law, correct? And sometimes some problems need knowledge of entropy. If you say that your system is isentropic, which is, or you say that your system is adiabatic and internally reversible, you know it's isentropic. It gives you hint between state 1 and state 2. Like in your homework, in last problem in your homework 8, what is stated? You have state 1, but you don't know state 2. So this is classical, your last problem from the homework, problem 8, it's classical problem from chapter 5, right? It looks like chapter 5. But you would not be able to solve it months ago. Why? Because you don't have enough knowledge about state 2, about exit. But now you know something. You know it's that your turbine operates in internally reversible manner, and it's adiabatic, so it's isentropic. So S1 is equal to S2. I tell you many times, read the text body. Your text gives you nice equations. Read the tank, V1 is equal to V2. Adiabatic, Q is 0. Isothermal, T is constant, T1 is equal to T2. Isobaric, or free piston motion, free piston cylinder, P1 is equal to P2. Eventually here we have isentropic, S1 is equal to S2. So that it is. Equation S1 is equal to S2 is not worse than big equation you have for 3 lines when you have balance equation for first law, right? Make sure you know how to get equations from the text. Again, you know how your exam will go, like exam 1 and 2, it will be posted, you can print it out, you can scan it, you can write it, type the text as before. And also you know that you will not have time, you really will not have time to think about something. So if you waste time on some problem, it means that something goes wrong. You should be straightforward, right? And remember that chapter 3 property tables are still backbone for the entire course. And I tell you something, if people ask me, what is more important, chapter 3 or chapter 7, entropy or property tables, you know, I will tell you tables. I will tell you, like, not pedagogic advice, but it's true. Imagine you did exam 1 and 2 brilliantly, but now you get stuck and you don't know entropy. May you pass this course? Well, I will tell you that it's questionable. But if you really know everything but chapter 7 and chapter 6, and you go to your final exam, maybe you will get C or B or D, but you will solve some problems. You will do many things. But if you don't know if you really learn entropy, but you don't remember property tables, you don't remember phase transitions, you don't remember first law, you don't remember chapter 3, 4, and 5, believe me, you will get F for your final because you will not be able to solve any single problem at all. In each problem you need it. And your brilliant knowledge about entropy will not help you. Does it make sense? Right? Okay, I believe you see my screen, and what I want to do now. I want now one thing. I really will have a short review lecture now. We don't have time to recall something, but I want to focus on mistakes that you are doing. Remember, I always talk about mistakes. I know what mistakes you are doing. I teach this course 11 times. It's my 11th time now. I taught it 10 times. I know typical mistakes. And it's a pity when I tell about mistakes at lectures, at review sessions. And when we grade you, we realize that you exactly do the same mistakes, many of you. Hopefully, those who don't attend my lectures, but anyway. So please don't do silly mistakes. Okay, so what you should know, if you look at the slide and you see my screen now, right? So what you should really know, what is your outline here? Basically, this is what I gave you topical overview last week. So you need to know second law. You need to, and when you're preparing, go through chapter 6, okay, and chapter 7 until subsection 6, until 7.6, until TDS relation. So what you need to know the various formulations of the second law: Kelvin, Planck, Clausius, entropy, and the identity that they're equivalent. right? You need to know power cycles. What is thermal efficiency and what is heat engine? Remember, heat engine is not just engine, it's abbreviation. Refrigeration and heat pump cycles, their coefficient of performance, right? How to calculate. You need to know what is reversible and irreversible process, including internally reversible and externally reversible. What are irreversibilities and what are the measure of irreversibilities? How we measure it, which is entropy. You should know Carnot principles, which says what is the maximal efficiency and formulas for them. And you know Carnot cycle as example. Don't confuse Carnot cycle and Carnot principles. Carnot is the same guy, but items are different, right? The same like don't confuse Clausius statement, Clausius integral, and Clausius inequality. Clausius was the same person, but items are different. In this exam, you really need to know some theory, some philosophy. It's really important. Only when you dive deep in this and understand, everything will be very simple. Now everything is still hard. That's why we have this exam. That's why we want to pick it up before the final. So you will know Clausius integral and inequality, which allowed us to define entropy. Remember why I write inequality. If you don't remember, it's good time to rehearse that lecture. Entropy generation and transfer, entropy increase principle, and entropy balance for a closed and for open system. Again, remember, we still talk about closed and open systems. And really not nice things that I realized at help sessions. That sometimes students, especially from other sessions, from Dr. Mabain's sessions, they ask me, okay, may I use this formula? Okay, if you don't know where formula come from, you better don't use it. You better think again, especially when you have homework. And so the really wrong scenario when you Google and say, okay, efficiency, find some formula and use it. That's why in the class, even in this class, online class, I try to derive some formulas. When I taught this in person, I derived much more on the blackboard. It's boring. I don't want you to remember derivations, but what you remember why it comes from. If you derive a formula, you understand why it comes from. So please remember, first, when you read the problem, see, is it closed or open system? Control C, mass or control volume? It's conceptual. If you don't know this, you have no chance to solve this problem. And when you know it, that's use correct formula. If there is mass transfer or not. If there is no mass transfer, it's one story. If there is mass transfer, another. And then think what formulas to use. Don't start solution with formula if you don't know where this formula comes from and what does it describe. So look, if you, now you see the slide, correct? So is there anything in this slide that you don't know? Briefly. If this is the case, now it's real time to rehearse that lecture and read the textbook. You must know everything what you see here and must know this deeply. If there is something that you don't know, you're in trouble. When I teach you in person and I see your eyes, at this point I can look at you and say, okay, you don't know this, you don't know this, let's talk, let's consider. I don't see your faces now. It's your task now to understand what you don't know and ask. Ask me, ask the TA, ask your friends, ask Google, read the text. But it's your task to know, are you flexible or not, right? Remember, when you talk second law, works in it's supplementary to first law. It does not replace. So key point, and we have this problem in your homework number 6, to make sure that first law works, that there is the first law is energy conservation. Overall, we have, remember, 4 laws of thermodynamics. Zeroth law, 1, zeros, first, second, and third. Zeroth law is simple equilibrium. If you have the same temperature with somebody, you're in thermal equilibrium. Third law, well, it's Nernst theorem, which states that entropy at absolute zero is zero. But first law, it's energy conservation, and second law, it's what we are talking about in this exam. But please remember, if they should work together, they should work both. And if first law is violated, if you have wrong energy conservation, don't consider second law. Second law can work. Second law can give you anything. Key point is first law. If first law works, then great. Then you will talk about second law, okay? Remember formulation. So what you have, Kelvin-Planck statement, which states about heat engine with one reservoir, Clausius statement, which states about refrigeration cycle, and entropy statement. And remember that that's how we introduce entropy. And again, don't confuse entropy statement. It simply states that entropy cannot be destroyed, right? That, again, classical mistake here that you may see. Well, Kelvin-Planck statement that in this device you need to have second reservoir. Everyone can write it. Clausius statement. Please don't say that it's impossible to transfer heat from cold to hot source. It's wrong, right? It's wrong. Your fridge does it. You should say that it's impossible to do it for free. Your refrigeration does not work for free. It should be another item here, another effect of transferring heat from cold to hot source. Heat goes directly from hot to cold. Ancient Greeks knew this. But to do it vice versa, how to do it? Ancient Greeks did not know, we knew it. We know it now, right? Okay. Entropy statement. Don't say that entropy does not decrease. Don't say that entropy change is positive. It's only for isolated system like our universe. Entropy can decrease. When you drink tea from the cup, entropy in this cup decrease. When you put gas or liquid into fridge, it will get frozen, its entropy will decrease. That's okay. The only point, entropy cannot be destroyed. Everybody remember this? That is called, so Kelvin-Planck statement simply says that it's impossible for any system to operate in such a manner that heat will be entirely converted into work. It's impossible. You should pay penalty according to second law. Second law tells you that nature does not want you to be like this. Nature does not want you to convert heat into work, right? And ancient Greeks thought it's impossible. We know it's possible, but you should pay penalty. And what is your penalty? Penalty that you should have second reservoir to reduce the heat. And another formulation that work over the cycle is non-positive. It's zero if you have a reversible cycle, and it's negative if you have irreversibility. Clausius statement says that it's impossible for any system to operate in such a way that the sole result, not the result, but sole result. Here, sole, so it's a key point, don't forget about it. Is the result will be transferring energy from cold to hot body. Otherwise, refrigerator, this is an example of refrigeration cycle when you have compressor, condenser, heat boiler, and throttling valve. So what happened here? You need compressor. You cannot work for free. That's impossible, right? That's what is stated. Your fridge does not work for free, but it may exist. That is Clausius statement. And you know the equivalent. What also you should remember? Thermal efficiency. Well, remember what is thermal efficiency from chapter 2. Thermal efficiency is desired over required. Okay, desired over required, nothing else. What is heat engine? So please understand, heat engine is not like engine in your car. It's maybe a heat engine, HE. It's any device converting heat into work. And what do we know about heat engine? What do we want from heat engine? We want work output. What do we need? QH. So the ratio is your thermal efficiency, right? So what do we know about thermal efficiency? Even from chapter 2, we knew that thermal efficiency is from 0 to 1, right? It cannot be more than 1 because the only part of energy can be converted. But now we know that it's not only less than 1, but it's less than some maximal value given by Carnot heat engine, right? So that is thermal efficiency. Is everything trivial what I'm talking now? It should be trivial for you. If you understand everything, it's great. If it's not trivial, that is your trouble here. Look here in detail and solve the respective problem. Okay? Refrigeration cycle. So what is refrigeration cycle? Idea about fridge transferring heat from cold to hot source. That's how it looks like. And here we have a concept of coefficient of performance, COP. For refrigeration cycle, we call it also beta. And so what do you want from your fridge in your kitchen? What do you want? You want your food to be cold, right? So you want to take heat out from its environment. So that is what you desire. So you desire QL. You desire to get heat from here. What do you require? You require work input, right? According to second law, it does not work for free. So coefficient of performance is QL over work input. That is the value. Remember, this value can be larger than 1. It's okay. It can be less than 1, can be larger than 1. It's okay. The only thing is it cannot be infinitely large because work input is finite. It should be here, right? because of second law. That is coefficient of performance. Why it can be larger than 1? Because I told you, you don't convert something. It's like if you're a very strong person, you can really take 1 ton of loading and put it on 8th floor. How you will do it? You will take elevator, you will take some cart. Your mass is 50 kilograms or 100, whatever you are. But you can bring ton upstairs. Why? Because you have some devices. The same story here. It's a card which helps you to bring something. That's why your coefficient is larger than 1. Now, what is heat pump? Heat pump, it's actually, picture should be similar. For heat pump, actually your fridge can work at heat pump. But the idea about it is the aim is different. Idea is the same, but aim is different. Because what heat pump does? Heat pumps actually make your house warm. So heat pump transfer heat from the street to your house. And at this point, what is the difference here? When you talk about fridge, you don't care about your kitchen. You talk about heat which goes from your fridge. When you talk about heat pump, you don't care about the street. You care only about what? You care about heat which goes into your room. So now what is desired? It is QH what is desired. And it is QL, not Q, what you get from the street, but it is QH what is desired, and still work input is required. So coefficient of performance for heat pump, it will be QH over work input. QH, not QL. That's the difference. And COP, and also we call it gamma. And coefficient of performance of heat pump is always larger than 1, larger than unity, okay? So that it is. And that's what you must remember, that's what you should understand. Also remember that if you have relation of coefficient performance of heat pump and refrigerator, it will be this relation, correct? Now, another point. Here we talk, and many people get confused sometimes here. Here we talk about absolute values. In all these formulas, all values are absolute, are positive, right? But at the same time, you may realize that when you talk about work input here, generally speaking, it's negative because you go counterclockwise. If you look at this cycle, it goes counterclockwise. So this work is negative. This work is done on the system. So we took absolute value, but logically it's negative. Well, if you talk about heat engine, it's clockwise, and work output is positive because it's done by the system. Again, don't confuse chapter 4 and chapter 2. Remember our convention. Work is done on the system is negative. Work is done by the system is positive. It's conceptual. Does it make sense? So that's what we discussed. That is a major point. That's what we need. Then we came to point of irreversibilities. Irreversibility is anything that make your process are not idealized. Like remember, heat transfers through finite temperature difference, spontaneous chemical reaction, spontaneous mixing, friction, dissipation, solving, inelastic deformation. Everything that can irreversible is something that you crush and you cannot go back. You dissolve sugar in liquid, you cannot just get straightforward this brick back. So the process we deal with, most of the process we deal with are irreversible. And the more irreversible they are, the less your efficiency will be. So it will be, and that's why actually, that's why we come to second law. So nature does not want irreversible process, even all of them are irreversible. Because all irreversible process is one step to thermal death of universe. So that's why nature asks you to pay penalty when you have it. And that's what happens. So you do have irreversibilities, and entropy, or to be more accurate, entropy generation is a measure of irreversibilities, entropy generation. And you may realize that the more irreversibilities you will have, the more entropy generation will be. Now, how to calculate this entropy generation? We'll talk later, but just from here you may realize there is no calculator how you go and see, okay, one irreversibility, second, so then you put it in a box. No formula like this. So to calculate entropy generation, you should write a balance equation and find all other terms, and then you will find how much you spend. Then you will find your entropy generation. Okay, and here you realize that the less irreversibility we have, the better, and we arrive to Carnot principles, Carnot realities. What is it? Remember, it's a very simple idea, like I told you about classical by Leo Tolstoy about happy families. I tell you the classical statement that all happy families are happy in the same manner. All unhappy families are unhappy in their own way, their way. And all unhappy families are less happy than happy families, right? Why we use this? The same story here. Happy family is our, like sane family, is our etalon. It's not us, but that's something we try to tend to be compared to. So that's what we check. Carnot principle says that as soon as you have two reservoirs at given temperatures and reservoirs are given by temperatures, that all reversible power cycles operating between the same reservoirs have the same thermal efficiency. And since they have the same, the thermal efficiency will depend on their temperatures only, correct? And first statement simply says that, okay, that all irreversible power cycles, they are worse. They are worse. So the efficiency is less than that of reversible. Right? Do you understand this? All reversible cycles are ideal. They have the same thermal efficiency. And all other realistic cycles have less efficiency, provided they operate between the same reservoirs. And what does it mean for us? Now we say that let me find one sane family, one template, and I investigate it. And then I will know about all other happy families and all other unhappy families. And then we come to idea about Carnot cycle. Why Carnot cycle? Because this is the simplest reversible cycle. There are many other cycles, but this is the simplest you may have. There is nothing simpler. And if you investigate this cycle and find its efficiency, then what you may say? That all other reversible cycles will have the same efficiency in terms of temperature. And all realistic cycles will have less efficiency. Does it make sense? And this is you must remember and you understand. So what is Carnot cycle? Two isotherms, two adiabat. What do we have? Again, you can start from any point, but generally speaking, what you have? First, you have heating of piston cylinder assembly for a closed system. This is process 1, 2. This is what? This is isothermal expansion. Temperature is constant, you expand. Then here, process B, you move out heating and you have adiabatic insulated expansion. Remember the difference between isothermal and adiabatic. It's two different items. I told you many times. Isothermal temperature is constant. Adiabatic, no heat transfer. It's not the same. When you cook something at 100 degrees Celsius, it's isothermal but not adiabatic. When you compress gas, it's adiabatic but not isothermal. Please remember. Okay, what we have next? Next, we have process 3. When we have cooling, you have cold device here, cold source, and you have isothermal constant temperature compression. And eventually you release your system and you have constant, constant heat, adiabatic compression. Reversible isothermal expansion, adiabatic expansion, isothermal compression, adiabatic compression. That's a must to know. That's what you should know. And basically that it is. And that is on the left-hand side, you see how Carnot cycle looks like. So heat comes in, this is work output, this is heat goes out to cold reservoir. And since it's reversible, you can put it counterclockwise, right? As you see on the right-hand side, on the right picture. And when you put it counterclockwise, it will be counterclockwise. It will be what? It will be heat pump or fridge. And remember, when I talk about Carnot principles, again, don't confuse again. If I ask you Carnot principles, write down Carnot principles. Don't say Carnot cycle. It's two different items. Carnot cycle is here. Carnot principles is here, right? So the same Carnot principles will work out for what? They will work out for heat pumps and refrigeration cycles. I can say the same conclusion, right? That all reversible heat pumps will have the same efficiency, provided they have the same reservoirs, and all other heat pumps will have less efficiency, correct? So that it is, that's what you may realize. That's how it looks like. Two isotherms, two adiabats. Make sure you know how to plot it, how to write it down. And this is PV diagram. And remember, we discussed in TS diagram, how it will look like in TS diagram. In TS diagram, it will be simple rectangle. Remember, and we did it in the class. And if you have TS diagram, it will be what? It will be just something like a rectangle, right? If you have TS, it's understandable because you have two isotherms and two adiabats. Okay. Now, so what you should remember about thermodynamic cycles, power cycles, convert heat to work, I recall it, fridge, and heat pump transfer heat. And so what you may see here, that's how they look like. And you remember these formulas, right? You remember these formulas. So basically what you see in all these cases, you have two equations to describe it. These are two equations, right? If you have two sign equality, you have two equations. You have two equations. So most likely when you have two equations and you have four variables here, right? So you need to know two of them to identify two others. True? You know two of them, you will identify two others. So that it is. And very often you don't know, you may have only one of them and you have question, where can I get something else? At this point, please read the text body. Because very often times it may be what? It may be Carnot cycle that you can compare. It may be stated it's reversible heat pump or Carnot heat pump or heat pump with maximal coefficient of performance. Maximal, reversible, Carnot. It gives you hint that it's here and you know these formulas. Maximal efficiency, maximal for beta, maximal for gamma, right? That's how we calculate. Everybody remembers this formula? Very important. These formulas are in Kelvin scale. 20% of you are going to do this mistake in your test, confusing Celsius and Kelvin scale. It should be in Kelvin. If you have it in Celsius, convert into Kelvin. These formulas are from absolute zero. That's how, remember how Kelvin identified absolute zero. He told that I need a new temperature scale at which heat relay ratio gives you temperature ratio. That's how we define absolute scale. That's Kelvin scale. Don't use Celsius here. And this gives you hint how to identify the nature of the process. It can be eta, beta, gamma, whatever it is. Please check. Please check what it is and state. Is it, what's the process you talk about? And say, if find your efficiency, which you have in reality, and find maximal, that is Carnot efficiency, and check. If yours is less than maximal, it's okay. So you deal with irreversible scenario, irreversible cycle, which may happen in practice. If your efficiency is equal to maximal, what can you say? It's theoretically possible. I would not recommend you to invest money in this, but theoretically it's possible. You cannot decline it. But if your efficiency looks like larger than Carnot efficiency, that's impossible. I told efficiency, but the same for beta and gamma. That's the way how you approach. That's one way. And in chapter 7, you have another way how to solve it by means of Clausius integral, right? Clausius, what is Clausius integral? Remember Clausius inequality? We developed through this integral. So that is Clausius integral. You calculated through sigma, remember? And you calculated here that if you calculated sigma as follows. Remember about this conventional sign minus. And what you have here, the same story like before. Sigma, actually, it's a measure of irreversibilities. Later, it will be called a measure of entropy. It's like dimension of entropy. The same story as you see here, you may do like this, calculate sigma. If sigma is positive, then there are irreversibilities, it's okay, you pay some penalty. If sigma is zero, it's theoretically possible, it's irreversible scenario, irreversible process. Eventually, if sigma is negative, that's impossible. You can get bonus tickets in my class, but you cannot get bonus tickets for best driving, right? It's impossible. And you remember how we arrived to Clausius inequality? This is Clausius inequality. Why I call it inequality in brackets, in parentheses? Because it may be equality if you talk about internally reversible scenario. So remember this. If you have integral dq over t is not, this integral is non-positive. I may ask this question in the exam. Please remember, it's non-positive. And it's negative in realistic scenario, it's zero if you have internally reversible process. That's Clausius inequality. Don't confuse with Clausius integral, don't confuse with Clausius statement. Clausius is the same guy, items are different. And why we need this? Because that allows us to define the entropy. Remember, so entropy is such a function which change is given by this. So it has the same units as specific heat, heat capacity, it's energy per temperature, but it's different item. And that's how we define. So that's what you remember. That's how we define entropy. And when you define delta S, you should find some reference frame. And our reference frame is very simple. We say that entropy is 0 at absolute 0. So that's what you should remember about entropy, about entropy generation. So I tell you 4 approach to entropy. Philosophical approach, my approach, personal approach, that you pay penalty according to second law. If you want to convert heat into work, if you want to transfer heat from cold to hot source, you should pay penalty. And currency in which you pay this penalty is entropy, also entropy generation. So entropy is not, so that's one approach. Second approach, you will have formula for it. Here is a formula. Third approach, entropy, especially specific entropy, it's an item from your tables. And whatever you did with U, H, and V, you should do with S. Specific entropy is item from your table. And all of them, and also, you know, entropy is measure of disorder. Like if you system is more free, its entropy is high. If system is more ordered, its entropy is less. That's why if you heat the system, you stimulate entropy, right? If you pressurize the system, you decrease entropy. It will be function of P and T like it should be. Now, what you must remember, I recall, entropy generation is that penalty that you pay. If police officer, if you drive and you get if you don't get any ticket, you can hide that you were driving. But if somebody stopped you and gave you ticket, the ticket was you. This ticket appeared from nothing, and you cannot get rid of it. If you cut it, if you don't pay it, you will get extra ticket and eventually will be jailed. So you will increase entropy, you increase your crime. You can ask your friend to pay your ticket for you, but you cannot destroy it, right? This ticket is with you. It appeared from nothing. And this ticket cannot be bonus ticket, right? This ticket cannot be negative. It's impossible that police officers stop you and say, okay, this is your award for best driving. No, this ticket is only your penalty. And if tomorrow and all the days after tomorrow you drive perfectly, this ticket is still with you. You cannot reimburse. So that's entropy generation. And your second law, entropy statement of the second law says that entropy generation is non-negative. Okay? Don't say that entropy cannot decrease. It can. You see in this picture, entropy can decrease. Somebody, if I take your ticket and pay instead of you, your ticket decrease. But I cannot crush it. That's the point. And it's very philosophical, because if entropy generation would be negative, it would mean that you can go from future to the past, right? Because all irreversibilities will become reversibilities. We go from birth to death. We cannot first die and then be born, right? Because of entropy generation. Entropy is the same property. So what is entropy? Entropy is exactly the same property like others, but it's not conserved. There is entropy balance, but there is no entropy conservation. Remember TS diagram. So in fact, in TS diagram, heat transfer, surface area here is heat transfer in TDS. That's why we need this TDS diagram. And if there is no entropy change, we call this process isentropic. What you see here is entropy balance for a closed system. Two important words, entropy balance and closed system. Entropy balance and closed system, okay? So there is no entropy conservation. Entropy can appear from nothing. Now, look here what we say, and we remember we discussed it in the class. So what we say here is in simple words. We say here that entropy change in a system, it will be entropy transfer through the boundaries. Like it will work. But unlike students in the room, we can produce new students in the class. We can produce entropy. Now, that it is. So there is entropy production term. But what is important here is that this term is non-negative. So entropy change, this value, can be positive, can be negative, can be zero, right? It's okay. It can be negative. It's okay. You can decrease your entropy. Second term, it's entropy due to heat transfer. Again, this term, it can be positive if you have heating. It can be negative if you have cooling. And it can be zero if it's a adiabatic system. But sigma or entropy generation is non-negative. That's the point. It can be zero if you have internal reversible process, otherwise it's positive. So that's what you realize. All other terms can be positive, negative, or zero. That is like this. And that's how you come to the question that it's positive or not. Right? Now, and remember, so from what we say from here. If you have internally reversible process and adiabatic, what does it mean? Let's say, let me write down some text here. If I have internally reversible process and I have adiabatic, then it's isentropic. Then it's isentropic. Isentropic. Why? Look here. What does it mean that my process is internally reversible? It means that there will be no sigma here. There will be no sigma term here, right? What does it mean that my system is adiabatic? No heat transfer. So if this is 0 and this is 0, this will be 0. But it's not vice versa. Okay? It's not vice versa. Because I may have isentropic process, this will be 0, this will be positive, and this will be negative. So I may have isentropic cooling, right? The temperature will go out here, it will be some entropy generation. I may have isentropic cooling, but I may not have isentropic heating. I may not have like this, right? Another point. Very often in engineering, we may neglect some terms, right? When we calculate gravity, we neglect the effect of moon and so on. So very often in engineering, if I say, if this value is 1000 kilojoule per Kelvin, and this value is 999, people say, let's neglect this term. Okay, this is not the case. Or let's say like this, if this is my 1000 and this is 1001, believe me, I cannot say that, okay, let's assume they are equal and this is 0. And let's assume that it's totally reversible. No. This value cannot be O minus 0.1 or 0.0001. Right? It's impossible. It means the system does not exist. You cannot be 0.1% pregnant or 0.01% dead or 0.01% you don't exist. It's impossible. It's not does not matter how small the sigma or how big the sigma. Sign is most important. If the sigma is negative, you did something wrong. The system does not exist. And of course, as we remember, it was good problem we solved in the class that system process did not exist adiabatically. You cannot go from state 1 to state 2 adiabatically. But when this is not 0, it may exist. Picture on the right show nothing but the same for in terms of derivatives. Exactly like you did before for energy. If you have steady system, you don't have this. If you have reversible system, you don't have this. If you don't have heat transfer, you have like this. Please remember. This is for closed system, okay? For open system, you extend this. Exactly like we did in chapter 5 of first law. What you see here, it's the entropy balance for what? For open system. Again, we say that is what? It's entropy transfer through boundaries and entropy production. You have this term because there is no entropy conservation, and this gain is non-negative. What you see here, entropy which comes in, entropy which comes out with mass, right? That's what you realize. Again, look here, if you have closed system, what does it mean closed system? Then you don't have these terms, you come back to previous case to closed system. So this is general form of the law. If you have adiabatic system, you would not have these terms. If you have steady system, you would not have this term. If you have reversible system, you don't have these terms. And so on, so on. That it is. If you don't have mass transfer, it's like this. Does it make sense? Okay. Very good. So that's all. At this point, I will close sharing screen and will stop. Will stop screen now, and I will stop